no sense. You're on a planet right now. You think you're in America? Zoom out. You're on a space rock floating in nothingness, infinite nothingness. And the infinite nothingness is expanding. That means endlessness is getting bigger. That makes no fucking sense. We all just act like it's normal. Like, oh, everything's made of molecules. Okay. Got it. I'll never think about that again. I'm made of molecules, you're made of molecules, the air between us, it's all made of molecules. That makes no fucking sense. These molecules know they're molecules. These molecules are like, I'm pee. That doesn't make any sense. This stool is made of molecules, the same molecules in my hand. In fact, some of the molecules in this stool went into me while I've been talking, and some that were me have gone into this stool. And you know, when I knock these molecules into these molecules, when we ask science, why don't they go through each other? You know what the answer is? We don't know. That doesn't make any fucking sense!
All right, so like Pete said, science sometimes doesn't make any sense, and quantum world can be even worse than that. So today, to deconstruct a little bit this whole quantum computing topic, we're going to go through a small intro, history, bits versus qubits. We're going to talk about some of the algorithms and applications, and then in the end we'll do a small recap for you guys to take home. So, quantum computing, what is it exactly? Is it just using quantum mechanics complex principles such as superposition or entanglement to be a cutting edge and revolutionary computational tech? Or better, it's just using quantum gates instead of logic gates to perform complex operations, or just not using bits, or just being a so big computer that it wouldn't fit in this room, needs super critical conditions to function, and you can use it to play Fortnite. So you're probably wondering, why then, right? So it all started with this guy. Does anybody know who he is? Richard Feynman, exactly. So he also appeared in the previous presentations. He's known as father of nanotech, father of quantum computing, father of everything. So we actually say in nanotech that all roads lead to Feynman, okay? So this guy is the big boss behind all this. And there was another one together with him. Do you know who he is? It's Yuri Manin. And these two guys together, they came up with some crazy cool ideas. So it all started around 1950s with the development, the big development of the concepts around quantum mechanics, right? And, but here we had no idea what we wanted to do with it. We were just exploring it and coming up with some crazy concepts and crazy theories around it. But then later on, much later on, Feynman said, hold my beer, I have an idea. Let's use quantum physics to come up with new computers. And then in '81, he came up with the Universal Quantum Simulator. Then much later on, you're going to see there's almost a cadency of 10 years between breakthroughs. There's Peter Shor coming up with an algorithm, and Love Grover also coming up with a quantum algorithm. We're going to talk a little bit in detail of the Peter Shor's one. And then in 2001, we have the first quantum cryptography network. So after that, 10 years later, we have the D-Waves quantum annealer. And almost 10 years later again, we have Google's quantum supremacy claim. And since then, so recent years, it's been a boom, okay? So all the big guys like Amazon, Google, Microsoft, IBM have been betting a lot of their money on this. So what is it exactly with quantum computing? So in classical computing, we have bits, right? And these bits can configure two states, 0 and 1. But in quantum computing, we don't use bits anymore. We use qubits, because everything has to have quantum in the name. And these qubits configure 0, 1, and everything in between. And the best part is it's simultaneously, whatever that means. So you probably heard about this famous cat, right? Have you heard about the Schrodinger's cat? At least you've seen it in Big Bang Theory or something like this. So to have these two states simultaneously, you basically have to use one of the most known principles from quantum mechanics, which is the principle of superposition. So just to give you a bit of context, because principle of superposition comes together with the Schrodinger's cat. This is just a theoretical experiment. No cats were harmed by Schrödinger, okay? Just to make that disclaimer. But basically, he put a cat in a box, which was probably pretty pleasing for the cat, because cats love boxes. And he puts venom, a poison, inside the box, and he connects this poison with an isotope. Long story short, doesn't matter what an isotope is. What you need to know is that the isotope has a 50-50% chance of being triggered and activating the poison, okay? So the box is closed. It's a cardboard box, so he has no idea if the cat is dead or alive, right? So until he checks the box, the cat is both dead and alive, right? Because he knows that by the time that he interferes with the box, he will be interfering with the system. So he might destroy the early stage. Maybe the cat was alive and he opens it and it's dead. Or the cat, well, the other way around is kind of hard, but he doesn't know that by opening the box, he's interfering with the system and he might lose the previous state, okay? So without opening the box, the cat is in the both states, dead and alive, and you have no idea which one it is. So before we go into the deep dive of that, we need to understand that qubits are different from bits, and they are obtained in a different way. So in the previous sessions, we heard that bits are basically transistors, and they are either on or off. And in qubits, it's slightly different. So we have one of the most known ones, which is the superconducting qubits. These are basically materials that have very special properties when they are in extreme environments, so super, super cold environments, and they carry currents without any resistance, okay? That's why superconducting, right? And these can be controlled by electrical fields. Another way of getting these qubits is the trapped ion qubits. So these are basically individual ions that are held captive in electromagnetic traps. These are both used, especially the superconducting, but these ones, the topological qubits, are actually the most promising ones. So the topological qubits are basically topological insulators, and by topological we mean that they are good conductors in the interior. They are insulators in the interior, but they are good conductors in the surface and edges. So that's why topological. And these are pretty robust qubits. They are very promising because they are more resistant to noise, to interference from the exterior. They are more robust. So you don't want to drop your quantum computer on the ground, but if you do with these ones, you might save a few qubits. Then we have my personal favorite, quantum dots, which are semiconducting nanoparticles that trap electrons. And the spin of the electron is the qubit, and it can be manipulated with electrical or magnetic fields. These are also pretty interesting, quantum dots. Then we have the first ones that came in early experiments, and the first ones to be tried out, which are the nuclear magnetic resonance qubits. These ones were the ones that were used in the beginning. They're not so relevant anymore. I mean, they're still interesting, but they're better ones. And last but not least, we have another one which is pretty interesting. I'm sorry for the people that don't see the presentation because I'm hiding it. But it's basically the photon qubits, which have the qubit encoded in the polarization state of the photon. So, you know, photons are lights, and we can manipulate them with optical components, such as lasers or nanotweezers, etc. These are also pretty cool. So, how does this all work? For 2 bits, you basically have 4 states, right? 0, 0, 0, 1, 1, 0, and 1, 1. But for qubits, we have a little bit of a difference. In the beginning, it doesn't look like a difference, but you will see why. So for 2 qubits, we have 4 states. So you're probably wondering, like, yeah, it's exactly as 2 bits, right? And it is, because basically these 4 states are the excitation levels of these qubits. That's why you also have 4 states. It can be both spin down, for example, which would be the ground, which would be your 0, 0, and so on and so forth. But the interesting part of the qubits is that you can have superposition of these energy levels, right? So they can be in all the states at the same time. So for this to work, you need to write some mathematical equations that define exactly the state. So you need 4 coefficients, which are nothing less than just the probability of being on each state, okay? So in the end, this has to be 100%, but until you have a defined state, they are in all states at the same time, right? And because of this, because you need these 4 coefficients, you need 4 additional pieces of information. So actually, for 2 qubits, for 4 states, you need 4 additional pieces of information, 4 additional bits, let's call it this way. So because of that, if you put this in perspective and you start making counts, so for 2 qubits, I have 4 bits of information, right? So if I add 1 more, I have 8 bits of information. For 4 qubits, I have 16, so on and so forth. So you can see that there's a relationship that is an exponential relationship. So for n qubits, I have 2 to the power of n bits. And this is pretty awesome when you step it up a notch and you use 300 qubits, which is a technology that we're not so far away from. And if you imagine what this is in number of bits, it's actually more than particles that there are in the universe. Okay, so this is how badass the quantum computers can be. Their power of computation is relying on those coefficients, which make them so much better. So where's the catch, right? So when we are working with qubits, there's also another principle that is important to understand, which is entanglement. And what is entanglement exactly? So first you have the superposition, right? And the other one is you have 2 qubits. And they can be physically far apart. They don't have to be connected. They can actually be far apart from each other, like this distance in the living room, like I am right with you guys right now. And one thing that entanglement does is if you change the state, or you observe and then you change the state of 1 qubit, you're automatically changing the state of the other one without being physically connected, okay? So you can entangle them in a way that when you define the state of the other, you define the state of the other one too, and this actually enhances the power of computation too. You'll see that further in the presentation. So we have superposition and entanglement, and this allows parallel computation, which is basically running several operations at the same time and different operations at the same time. So in quantum computing, the objective is not to, the operation itself is not faster, but the amount of operations to get to the final result will be faster, because you will do multiple operations and less operations maybe to get to your final result. But the operation itself doesn't have to be faster, okay? But there is a catch. When you make the observation, like I said, with the cat, you lose the initial state. When you check the qubits value and you fixate them in zeros and ones, you will lose the previous state. So you will lose information. So superposition states are not measurable, right? We cannot measure the in-between. In the end, when we measure, it's always going to be 0 or 1. So what we have to do, and this is the crazy part, is we have to design the logical system to point you to a state that you can measure, and it has to be the state that you want. So yes, that is impossible. So here comes the crazy part, right? So quantum computers, that's one of the reasons why quantum computers will not replace classical computers, only for specific things, okay? So let's talk about now the fundamental building blocks of quantum circuits that are used to manipulate the qubits and perform the operations. So you're familiar with logic gates, or at least you've heard the AND, OR, SHOR, NOR, etc. So in quantum computing, because nothing can be easy in the quantum world, those logic gates are much crazier. So they are basically matrix elements, and they are the ones that are going to perform these operations to change the states of the qubits. So as you can see, these are not very pleasing logic gates, right? We have one that is actually similar to a NOT, which is just inverting the state. But besides that, all of them require a little bit of patience. But these are the ones that are used to define the qubit if we want them in 0, 1, 2, 3, 4, etc. So now let's talk about one of the most famous quantum algorithms, which was defined by this very nice guy, Peter Shor. He looks very happy. And we're going to think about how quantum computers can factorize a product of 2 primes in a much faster way. So imagine that for you to understand what is the application of this, I need to make a parenthesis, which is, you know, when you send a message in WhatsApp and it says your message is encrypted point to point, blah, blah, blah. So basically everything that we share is encrypted. And basically what they are using is a key that I have. So I have my own key, which are basically prime numbers. And I will cryptify, like my message, I will encrypt it using my numbers. And when I want you to read my message, I have to share the numbers that I've used. But the funny thing is, so if you have the numbers, it's very easy to decrypt it. But actually there's a way to do this. Of course, our computers cannot really do this, but quantum computers could. So basically what we do is the Peter Shor's quantum algorithm, which is, we have n, which is an integer, which is my message, okay? N is my message, it's encrypted, it's a product of 2 prime numbers. But you don't know the prime numbers that I used to encrypt it. You just get the n. Okay, it's just a value. And what I'm gonna do is this crazy approach to get to the prime numbers that were used to obtain n and to decrypt the message. So what I'm gonna do is I'm going to make a wild guess of g, another number, okay? And I know that g multiplied by itself a number of times will get to this rule, which is m, it's just some factor multiplying to n. Then we have n plus 1. Okay, it looks pretty easy, right? But the problem is when we're talking about these messages, these encrypted messages, we're talking about very, very large numbers. So when we have to then go to do the rest of it, it's going to get wild. But fun fact in the end of the masterclass, if you guys want to test the Shor algorithm with me and I check it with smaller numbers, I can explain it to you. So what we're going to do in the first step is take a wild guess of G that should be smaller than N and doesn't have to share any factors with N. Then we know that G multiplied to by itself will follow this rule, okay? So we need to find what is R that follows this rule. So what we're going to do is literally test G to the power of 0, 1, 2, 3, 4, 5, etc. And we're going to find out that this divided by N, the remainder follows a pattern, follows a cycle. It's 1, then has a bunch of numbers, then it's 1 again, then a bunch of numbers, then it's 1 again. And when it's 1 again, you have found your R. Sounds pretty simple, right? Of course, once again, sounds pretty simple when we're talking about small numbers. When we're talking about 600 character number, it's not so easy. But what we do is we find R, which is basically just this path, so this cycle. And when it's 1 again, we found R. So we're going to substitute it there. And we're going to find two numbers, because remember what I said is the product of two integers, right? So we have each parcel, so each part, so basically what we did is put everything here to isolate M and N, and basically you get two factors, and these are going to be your two prime numbers, basically. And what we do then is we apply Euclid's algorithm, far-fetched, blah, 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 blah. If you want to get into details, I can explain it later. But in the end, what we're going to get is precisely the two common divisors of these big numbers that you get are your prime numbers to get N. And you crack the code. This is pretty insane, right? It looks so simple, it looks so obvious, but of course, when we're talking about big encryption systems, it's not like 77 or something like this. It's much higher numbers, so big that Excel cannot do it, okay? Guys, I've tried it. So basically, this part is where our quantum computers are much faster. So they are not faster in making wild guesses or even calculating this part, but they are much faster in this section, because when you put the power on G, so when you're trying 0, 1, 2, 3, 4, 5, you're gonna get numbers that are just insane to work with. And these are the kind of operations where our computers are super fast, finding this cycle, finding this periodicity, because R is basically just a period for which you have ones again, so this cycle. And this is exactly what they do. So how do we do this? This is going to sound crazy now, but how do we do this using a quantum computer? Is you need two sets of qubits. And in one of the sets of the qubits, we are going to be working with this part, so the exponentials, and then this part. And then on this other set of qubits, we're going to be storing the remainders that are important parts to basically fulfill the algorithm. And then what we do is we entangle them, the two sets. And we're gonna find the cycle. So when we afterwards make observations, we're gonna find our R, for which the period is set by. And like this, we can easily find our R for numbers that are freaking huge, because it is testing at the same time multiple numbers to try to fulfill the equation. Of course, I'm simplifying here because there's a quantum Fourier transform in the middle, but I'm not going to get into detail with this one. So of course, if they can factorize, they can decrypt, right? So the problem is exactly that. So most of our implementations of RSA, which is the most common encryption algorithm, they use 2048-bit keys, which is equivalent of a 617-digit long number. So, of course, like I said, Excel cannot do it. Our normal computers cannot do it. They would take billions of years. I think they would take more years than our sun has. So I think that we wouldn't be very successful with it. But if we use 10,000 qubits, faulty tolerance, so we have to have redundancy and so on with the technology that we have now. But if we have 10,000 faulty tolerant qubits, we crack it in 104 days. And you're probably wondering, like, 104 days, that's a lot. Okay, so let's see what our experts think about this. But anyways, Shor algorithm demonstrated that some of these encryption methods can be broken efficiently and by a quantum computer, and this represents a huge threat to cybersecurity, okay? But we're going to talk about further on in the presentation that there are already alternatives and people are already betting on stronger ways for cybersecurity. And also we're going to have another presentation focused on cybersecurity, which is in 2 weeks from now. So also be sure to check that one. We have another approach to cracking stuff, which is the Grover's algorithm. But this one is more of a brute force approach, which is you don't try to crack, you try to find it. And basically, the Grover's algorithm is a search algorithm that goes through large databases and tries to find passwords and keys. So whatever combination of characters that has this pattern that looks like passwords or keys, Grover's algorithm can try to find it. And one of the things that we do nowadays is store now, decrypt later. We've been doing that a lot because we know that nowadays we don't have the capacity to decrypt it, but later on we will have. So, and you have data now that in 10 years from now it's still valuable, and so you want to crack it later. And let's talk about what the experts say. So there was an inquiry to experts that are close to experiments, and they basically asked them, okay, in 5, 10, 15, 20, or 30 years, how many quantum computers we are going to have that are able to crack RSA in 24 hours. And in 5 years, we have at least one quantum computer that is going to be able to do it in a 50-50% chance. That's already pretty high. 5 years. And in 30 years, 9 quantum computers will have above 99% chances of being able to crack RSA in less than 24 hours. So if we don't start working on this now, we're pretty much screwed. But if you want to know more about this, you have the 2021 Quantum Threats Timeline Report from the Global Risk Institute, and this is pretty interesting. You can get some very interesting insights in this report. So besides trying to crack passwords from people, what is the main applications of quantum computing? So of course we have one which is the most known one, which is optimization problems. So trying to find the closest path or the fastest path from point A to point B. So the other ones are, of course, cryptography and secure computing, which is basically trying to do the opposite of what we were showing just now. So trying to encrypt in better ways. So it's not, so if somebody else is trying to decrypt your message with the quantum computing, you're in the front with the quantum computing trying to encrypt faster, okay? Basically, that's how it works. And then we have chemical modulation and molecular simulation. So when we run, in the biochemistry field, when we try to run models to predict the behavior of big molecules or protein folding or whatever, our computers burn. Like we have to put candles and make a ritual to see if the simulation is going to run, and it's probably not going to run. So this is one of the things where quantum computing can actually help. IBM, so all of these are actually IBM links. You can check it later. The quantum chemistry is a concept that IBM was pretty strong with. They started presenting it in 2019. They were in Lisbon presenting it, actually, and it sounded pretty cool. Then we have also quantum machine learning. So here we're basically doing a joint venture between quantum computers and AI and machine learning. So basically what we do is help the models being trained. Okay, so quantum computers can process large quantities of data and run a lot of operations at the same time, and we use them to feed the machine learning mechanisms and to train them. And then we have something very interesting, which is quantum finance. And this is a very interesting one, because of course they state that quantum finance is to better react to the volatility of the finance sector. But honestly, I think they just want to predict the stock market, okay? And they want to know where to bet their money. And basically, the cool thing about this one is that stock market has tendencies, right? And the problem is we need such a big amount of data to be able to predict just an inch of what is going to happen in the financial sector, that maybe if we have something that has the capacity to parallel computing and all this and process way bigger amounts of data, maybe we can predict a bit more than just an inch. So what are the current challenges of quantum computing? So one of the things that is really complicated is qubit quality and error correction. Like I said, I mentioned more than once the faulty tolerance, because there's no such thing. I mean, the topological qubits are already pretty resilient physically, and they're very good, very tolerant to noise and so on. But still, it's a technology that it's very complicated. Actually, here we have 4 qubits. No, a few more than 4 qubits. They're basically these tiny things here. And the whole process of fabricating them and the whole process of setting up a big quantum computer, it's not easy. Actually, you can see it here in this image. This is a laboratory. This is IBM's laboratory with the quantum computers, and you actually also need like these platforms to prevent any kind of vibration. You basically sneeze next to them and you lose everything that you were working on. And so scalability, obviously, it's also a problem, right? So after that, we have the quantum software and algorithms. Like I showed you, like the logic gates are not our trivial logic gates, right? They're mathematically exhausting. And also when you have like this full entanglement, I was just showing 2 qubits, right? And you had those 4 states with those crazy cat equations. And so imagine when you have a full state of superposition and entanglement of 300 qubits. Okay, so you can imagine, and you have to be able to define the equation and the coefficients for all of them. So you can understand that it gets pretty crazy, pretty fast. So we need to have crazy guys to work on that too. Then we have interface with classical computers. We were never strong on that. I mean, we have problems interfacing Macs with Windows, right? So of course we would have problems interfacing quantum computers with normal computers. And this is also something we have to work on. Then we have costs. So together with the production of quantum hardware and the scalability, it also comes it's all related that the costs, I mean, this is all gold, right? It's very pretty, right? One thing is we have to be for sure is that the quantum computers are freaking marvelous. They're just beautiful. It looks like those sci-fi movies that are very interesting, right? So of course, if you have something that is literally dipped in gold, you're gonna have costs, and you're gonna have problems with that. And then ethical and regulatory issues. Guys, I just told you how to crack passwords. So of course, there is ethical and regulatory issues. Like I said before, what we are doing already is to store now to decrypt later. So we need to come up with the regulation and the laws to prevent that from happening, okay? Then we have operation environment. Like I just mentioned, as you can see, we're not going to have quantum computers for everybody, okay? We're gonna have a set of quantum computers feeding the needs of everybody. Because we're not going to have one of these big boys in our living room like we have these ones, okay? So a quantum computer is not a personal computer, and they need very specific conditions to work, especially if we go for the superconducting ones. All of this is like super ultra cold, like to 4 kelvins and whatever, so it's a pretty complex operating environment. And then we have competition. It might not sound very direct, but actually neural networks present and neuromorphic technologies present a bit of a competition to quantum computing, but they can also be complementing technologies, like I showed you before. So, but anyways, neuromorphic technologies and so anything that is brain mimicking can present a competition because it can also work on operations and do operations much faster. Then we have the real-world applications. So basically, so far I have showed you niche applications, right? So it's for finance, it's for chemistry. So we also, if we want to make a statement in the market, we need to find real-world applications. So normal people want to use some time in a quantum computer to do something. So why not trying it, right? There is these crazy guys from Amazon decided to take quantum computing to the market, and they defined this new concept of quantum computing as a service. And you can actually try it with Amazon Braket. Amazon Braket is based on several quantum computers from Oxford Quantum Circuits. They are a spin-off company from Oxford University, and they have Lucy, and you can actually buy time in Lucy. And actually the connection to Lucy is pretty straightforward. You basically use Python SDK and or developer frameworks like Pennylane and Qiskit. I haven't tried them, so I haven't tried Lucy yet. I haven't tried Amazon Braket. But you can buy time in it to run your algorithms. And they actually came up with another tool, which is CAT, which is a validation. It's an open source Python project, and it's a validation of your algorithm before you run it. So here you're paying, right? So you don't want to lose time in running faulty algorithms. So what you're going to do before is to check your algorithm with CAT, see if it's bulletproof, and then you will use it in Amazon Braket. Then another guys that are doing something pretty crazy about this is precisely combining AI with quantum computing, right? So these guys are working on security, quantum sensing, simulation, etc., and also trying to remove the complexity of cryptographic libraries for developers, and they are already trying to make a big statement in the market. So these are also some guys that are very interesting, and follow them to check what they're up to. So final notes, basically just a recap between about everything we talked about between classical computing and quantum computing. We have in classical computing transistors that can be on or off, 0 or 1. But in quantum computing we have qubits that can be 0, 1, and everything in between, or 0 and 1 at the same time. Okay? So then we have, in classical computing, the power increases linearly. So one more transistor, one more bit. And actually, in quantum computing, it increases exponentially. Then we have, in classical computers, they have low error rates, and they can operate anywhere. You can literally throw them in the ground, and if you're lucky, they will be functioning still. But please don't throw a quantum computer on the ground, because certainly it won't work. It needs highly critical conditions to function. Then the everyday tasks are going to still be done in classical computing. Actually, the Euclid's part of the algorithm that I showed you, you come back to your normal computing, to your normal computer to do so. So there's only parts that will be done in the quantum computer because they are much faster for optimization, operations, parallel computing, and so on, and simulations, but the rest will still be done in our day-to-day computers. And that's basically it. So thank you so much for your presence here today. Stay curious, and I hope you have questions. Thank you. Okay, so any question? Okay.
Hi. My question is, there is already a quantum computer working already. It's not theoretical. Okay. And where are the first computers? Where were they invented? Yeah. It seems a bit dangerous. Like I imagine it's Amazon or there's Google companies, and they have a lot of power. Yeah. And the Chinese, I think.
So that's exactly, that's a very interesting question, because who holds the power? Always the same guys, right? So who has the quantum computers? IBM, Google, Microsoft, Amazon, and these are, and also like Amazon has them through Oxford Quantum Circuits, which is a spin-off of the Oxford University, but they are already commercializing them, okay? And even if they don't present the risk, you can buy time in a quantum computer, right? So, of course, the algorithms are always reviewed and so on, but anybody can access a quantum computer already. And I think that most people don't know that. But basically, you can already access and run your algorithms there. Of course, they are reviewed and fact-checked and everything, but still, yes. And the big guys are the ones holding the quantum computers. More questions?
Thank you. Do you think that if, let's say, we come up with a room temperature superconducting material, do you think we could get to the point where we have a piece of quantum computing in normal computers, like we have dedicated GPUs for graphical processing? Do you think we could reach these states?
So the important part of the quantum computer is not only the qubits that are here, but it's the whole like noise reduction and redundancy and everything that we have around it. That's why it makes it so big, right? And also for you to have to create the entanglement and to do all these crazy operations, you need to always have a setup that so far looks like this. Because if you only have one qubit, and if you don't have the whole structure, it's not going to be a big deal. And yeah, so one of the things also is that the way you process and the way you change the states of the qubits, it's not as trivial as you change the bits of a transistor, right? Transistor is just it's voltage and current, and it's pretty straightforward. But for qubits, it's a little bit different. also, when you want to run the whole logic operation with quantum gates, you need a different kind of manipulation. So if you go for photons, you need optical elements and so on. So right now, I think it's still far-fetched that we are going to have pieces of quantum computer, but we have access to them anyways. So you don't actually need to have them physically with you. You will just have access to them. Jesus, so many questions. Okay, I think it was here.
Thank you. Very good presentation. I really enjoyed it. I have multiple questions because you already pointed on this picture, so specifically about this guy. How many qubits does it have and what kind of qubits does it have? That's one question, just like talk about this picture. I guess it's a famous one or something, I don't know. And another question is like, what is the state of jobs in quantum computing in Portugal, specifically at the moment? Like what kind of, yes, this is interesting for me. Like what kind of positions, quantum computing, machine learning engineer, or like software or physicist, quantum researcher? So can you please talk a little bit about that? Thank you so much.
Cool. I actually brought the image to show you a bit on this. So this is IBM's quantum computer, and it's a superconducting one. So there it is. This is basically the anatomy of the quantum computer. And these are the qubits, like I showed in the other picture, and they are basically here, which is this here, and which is the equivalent to that little piece that I was showing you. I'm thinking that this one has around like maybe 10 to 20 qubits, not much, not many qubits. I'm not 100% sure of which quantum computer this is, but they have around that. Like the maximum that we have is like 100 qubits. IBM is trying to come up with 400 qubits or 300 qubits. So the whole thing that I showed you of 10,000 fault tolerant qubits is still going to take some time, okay? But we are speeding up the process. Now regarding the jobs, you won't be lucky in Portugal, of course. For a reason I work in IT. Basically, we have, in these fields, you need a lot of people from different areas. You need a lot of IT for the whole software behind it, the whole noise cancelling and processing of the signals and so on. And then also the algorithms to run. Like, you cannot just go to the quantum computer and say, please give me 1 + 1. Of course, you need big algorithms that actually do something, and it's worth it. So you need IT, you need a lot of physicists, you need electrotechnical people, you need, mathematicians, so you need a little bit of everybody. So it takes a village to raise a quantum computer. Yeah, and that's, Carol, you also have a question.
Thank you. We have a question on the chat. It's actually... No, I think it's a student, actually, André Hernandez, your colleague, yes. So, this is a basic one, I think. Because of entanglement, do you think we would be able to communicate anywhere in the universe in literally no time? So if someone goes light years away from Earth, also, what's the meaning of life? Simple.
The meaning of life is 42. That one is easy, but the other one is actually a bit more complex. For you to have entanglement and for you to have these kinds of particles interacting, so you need to be able to control spins. We're talking about electrons, okay? And we're talking about photons. And we need to have them in complete vacuum. There's no particles interacting with them. The second there is one particle interacting with them, gone, okay? So these qubits, these whole processing units, these whole things, for you to achieve a qubit and be able to manipulate it, you have to have very, very specific conditions. So of course, you won't be able to communicate qubits throughout the universe, although it would be pretty cool. I mean, the particles are actually interacting, right? Like Pete said in the beginning, the molecules that are in me went to you and vice versa, the electrons too. There's actually crazy statements saying that there's only one electron in the whole universe and this electron is doing the service for everybody. But it's a cool idea, but we're not yet there, and definitely not able to communicate. It would have been handy sometimes, actually.
I had a question, but now you kind of answered. It was I thought about the normal computers when they first showed up. They were the size of a wall. They were gigantic, and everybody was saying they will not change, and you need a lot of people to work on them, and everything that you said. So my first question was, how realistic would it be for in 50 years for us to have, our own personal computers? But then you said, in vacuum, you need two molecules in vacuum, so that's impossible right now. And I think in 50 years as well, each person to have something like that. So my question is, in how long would it take, and how many quantum computers would it take for everyone to be connected to a quantum computer, so they can work, and instead of having their own laptop, they have a computer that is connected to a quantum computer somewhere else?
To be honest, I don't know exactly how many people can be connected to one single quantum computer at the moment. It's working more of a cloud-based service. So you probably have like these nodes and so on to run your applications and so on. But I'm not 100% sure how many people is like the limit. Also because I think that we haven't really reached the threshold of people that can that use a quantum computer at the same time. But for the amount of quantum computers that we have at the moment and their capacity of processing for the needs of the people that are in the fields, it's already pretty good. So in maybe 50 years, or not 50, but in maybe 10 years, it's going to be even more. So I think that it's going to be more a matter of price than a matter of capacity, because then you renting time, computational power or time in a quantum computer is probably going to be a bit more expensive than just a cloud service from Amazon.
So my question is related with the fields that you said that probably will be most useful for quantum computing. So which one do you actually feel it's the one that's going to get more leaps faster? The second thing is, how exactly do you so you have the quantum bits, but how exactly do you do that? Because in the previous presentations we talked about lithography and so on. So how do exactly do you make a, let's call it a quantum processor of some sorts?
Okay, so the field that I think that is going to really profit from quantum computing is it's actually two. It's machine learning, AI, and actually I've been exploring a little bit this topic, and that's why I'm so passionate about quantum computing, because I'm also interested in like brain-machine interfaces and neuromorphic and stuff like this. So having a badass computer behind it, running the data to feed the algorithms, so the learning mechanisms, it's going to be pretty cool, right? Of course, we would need not faulty data or unbiased data and blah, 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 blah. Then we have all the issues regarding AI, right? But if we have a computer, a quantum computer helping or teaching this machine learning mechanism, then I think it's going to be pretty cool. And also chemistry, like for sure, like drugs development, protein folding, etc., like development of vaccines and so on, like behavior of molecules. I think it's going to be really, it's most needed, and also I think it's going to be very profitable for them. Then how do we achieve qubits? I'm going to focus on my favorite ones, quantum dots. So quantum dots are the semiconducting nanoparticles. They're actually the sizes between 0 and 10 nanometers. Okay, so we're talking about a few atoms side by side. And they have these very specific crystal structure. In my case, I was working with perovskite, which is like, it's literally like a tiny cube, and you have an atom in each vertex, then you have one in the center, then one in each face. So if you imagine like a cube, you have an atom in these positions. And I spent 6 months of my life trying to produce them. I managed, but they are not easy. Not one, like a bunch of quantum dots, but then the problem is always like they're very unstable, they die very fast, they were not like stable, dried. You always needed like this very specific way of obtaining them. But this is the specific type of quantum dots that I was using. There are others that are much easier to work with, and those are the ones that they use here for these type of processing. But basically, the rest is some of the ways to obtain them. I think I have a picture here. You can see that it's pretty similar to the technologies that were used for nanotechnology. So it's etching and so on. So the whole rest of the processing is pretty similar. Only for the qubit part, it's going to be different. But it's heavy atom effects and so on. So it's really not only physics, but also a bit of chemistry to obtain them. And it depends on the type of quantum of qubit that you're using. Let me see here, we have the list. Yeah, so the quantum dots are the ones that I was talking about, and basically they can trap electrons, and they do these jumps between the energy states, and the spin is the one that is being controlled. Then the superconducting ones are just very specific materials that are pretty, not normal, but basic, and under the right conditions, they have these properties. So it's not something super crazy. Yeah, and that's pretty much it.
You were saying that two of the main difficulties were scalability and error correction. How does the error correction work? Is it also, like, do you do it in qubits, or is it like externally? And secondly, if I want to read more about AI and algorithms, like quantum algorithms, is there anything regarding this, or what is the most interesting algorithm?
So one of them that I tell you to really investigate is the Peter Shor's algorithm, which is the quantum algorithm that kind of started it all. This is also a fun fact that I want to show you later. But the Peter Shor's algorithm, it's very well explained in the internet, like YouTube videos explaining like step by step of how to do it. But also the pages from IBM that I showed you before, they have their own publications and the research work on this field. So you can also deep dive into specific applications like chemistry, finance, machine learning. So if you go to the website of IBM or you literally search for quantum chemistry IBM, you will get their publications, and you can check a bit more there. Yeah, and what was the other question? Error correction, exactly. So the error correction happens in two different ways. One of them is redundancy, so you have to have multiple qubits, and some of them are not really operating, they're just redundant systems. And the other way is a lot of signal processing, a lot. And algorithms have to be prepared for this. And actually, there are going to be times that you don't obtain a result, and you have to try it again and again and again until you actually get to a result that you know that it's what we are looking for. So it happens in two different ways, or more like three different ways. You have the physical redundancy, so you have the redundancy of qubits, you have the whole noise cancelling and so on, and processing and redundant systems, and then you have the algorithm part, which is the IT part, doing again a little bit of that. So it happens in basically three different ways.
Given their computational power, what role do you think they could play in scientific investigations? Because that's a really important part.
They're already playing a very important part in it. So, for example, in the quantum chemistry thing from IBM, so they can do prediction, like behavior prediction of molecules, of proteins, and so on, and also of drugs. So this is already being a big thing, and essentially the whole simulation part. So when we have, for example, if we want to predict the behavior of a new photovoltaic cell, for example, and we have to run loads of modules to predict like the yield and so on, and efficiency and so on, we can actually run these big simulations in those computers. So in every field that you need to run simulations to predict the behavior of something, they are going to help you. Of course, if it's something that takes a lot of time and needs parallel processing, it's a good bet to use one like this.
So how can you not observe qubits? Because if you have like equipment connected to it and it has the energy, like it knows what's happening with the qubits, it's observing already, right? So how can you not observe a qubit?
Oh, this is a pretty interesting question. We're entering the the deep quantum physics part. So actually, I'm going to give you the example of the photons. So we know that light behaves in two different ways, like it can be particle or can be a wave, and they can actually sense if they are being measured or not. So the way these qubits are set up is, this part is a bit more complex, and honestly not even me know exactly how it works. But basically when you have these entanglement positions or superposition, you're not interfering with the system somehow. So you're not reading the signal. You're not interfering with the quantum dot. Only when you make a single measurement and you pick up one at each time. You don't pick up all of them at the same time. No, the computer. So this all goes to the signal. So actually here you're not doing anything. So this is the whole setup of reprocessing, and this is the final read, of course. So this is where it's going to be read by the technician. But all of this, so from here, it's getting the waves, and then all the Fourier transform, quantum Fourier transforms and whatever, it's extracting the signal from there, and then it's getting results and states. But first there's a whole processing of the signal that you're getting. But because what you're getting basically is just wave sound, wave signals. Yeah. More questions?
When you were showing the gates, I know all of them except the last one, the biggest matrix. What was the last one? The starting with T2 or something. I don't remember the name. Yeah. Yeah. So how many qubits? Oh, but this one, okay. Okay. It's Toffoli, is it a name of a person or something? Okay. Anyway, thank you.
This is called also
CC not.
yeah, controlled NOT gate. So it's basically this one, controlled by two controls and a NOT. So controlled NOT gate. It's a mixture between those two. Yeah. And yeah, more questions? Jesus! But that's what I like. I don't
When we are talking about quantum physics and quantum mathematics, we're always talking about probabilities and how the signals are flowing through one another. How can you predict with quantum bits? I kind of lost.
So it's exactly in that part where I said that you have to design the system to point you to something that you can measure, right? Because the whole, you know, when you're measuring those coefficients, which is basically the probability of being in each state and so on, in the end, it's always going to point to one specific state, 0 or 1. You cannot measure the in-between, okay? So when you want to extract something out of these superposition states and this entanglement, you have to redesign, and that's why the quantum computer is much more complex. You have to redesign the system in a way that it points to the states that you want to retrieve. And so prediction, I think it's also one of the issues, because often you set up the qubits in the right states, you run the operations, so you know more or less that in the end it's going to be in the position that you want to have. But because they are not faulty tolerant, so they have faults, it might happen that one of them misses or just broken state or whatever, and you cannot measure it. So I think it's not really a matter of prediction, it's more a matter of having redundancy and so on, so that you can get the final state that you want.
I think we didn't talk about this specific topic, but is the quantum computer a spin-off of an analog computer?
Can the quantum computer? Yeah, so in the sense that you are reading signals and you have to apply the quantum Fourier transform and so on to actually extract the different signals that it's giving you, because when you have an entanglement state or a superposition state, you're receiving the signals from all the qubits, right? And then what you have to do is to extract each and one of them to find the position and find like the coefficients, and then it's a matter of always like factors times the position, or it's like this cat thing. So I'm not really into the analog computers, but I think that it might have its resemblances, yes, because what you're doing is basically just reading wave signals.
Are there more questions? Just because, maybe. Okay. Last question.
I mean, with traditional computer, you have all these gates, And I'm just wondering how it connects the picture that you showed before with the gates and the qubits. Like, do you have to arrange the qubit to become one of these gates? Or is it like really like you just, it depends on how you program or how you set the starting case of the...
So usually when you're running an algorithm, you start with the qubits at state 0, and then you apply the quantum gates to set them in the position that you want, in the states that you want. For example, when we were talking about finding R, right? You start with the second set of qubits all in the position of 0 state, and the other ones will be 0, 1, 2, 3, 4, 5, which is all the R's that you want to try out, right? And to flip the quantum, the qubit from 0 to 1, you have to do like one of the logic gates, and then for 2, 3, and 4, it's going to be a combination usually of Hadamard and X gate. So and like this, you're gonna flip like the states and change them and put them in the state that you want. So you start them in like ground, and then you do all the logical operations to put them in the state that you want. Okay, just to finalize, I wanted to show you guys something. If you guys are geeked to that point, you can actually wear superconducting rings. This is a pretty interesting brand. The prices are completely prohibitive, but these guys basically grabbed the garbage from the superconducting production stuff, and they made rings out of it, and you can actually see like the copper appearing in between like this grain limits and so on, and they made a pretty fancy thing out of the garbage from the superconducting materials. And to finalize, next week we're gonna have Future of AI hardware. Azal, she's a colleague from the same institute and where I used to study and work, and she's really focused on brain mimicking and alternatives to transistors as for AI, and this is going to be a pretty interesting talk too. And then another one that is very complementing these two fields of quantum and AI, it's with Professor Ana Ferreira in Porto. It's going to be in Porto, in Escola 42 from Porto, about cybersecurity and how do all of these technologies relate to it. And I think that's it. And also, if you guys are curious about the algorithm, the Shores one, you can just come to me after this, and we can check it. Thank you, everybody. It was a pleasure.
Thank you so much, everyone who watched also on streaming, and be sure to join our next masterclass. Thank you, Carolina. It was amazing. Thank you so much. Bye-bye.